So this is lecture 4 in a series on signal processing. It's an introductory course. You can find all the other lectures on a playlist that I'm going to be putting together. 32 lectures in total, meant as an introduction to how we might think about signals and the mathematical background you need to start understanding what you want to be thinking about when you take signals generically from inputs to outputs in many physical systems. So this lecture is going to focus on two very important functions. One is the impulse function and the other is the step function. In particular, we want to think of this object called the Dirac delta function. The Dirac delta function was invented by Paul Dirac to represent essentially an impulse, as I'll describe it here, into the system. In other words, a kick to the system. And we want to understand the response of the system to that kick, and we can learn quite a bit about our system by doing this. So it's a rich mathematical framework, and this starts setting up a way that we can start thinking about interrogating our system through interacting with it. So it really comes down to this basic concept. You want to learn something about your system. One way to do that, kick it. Kick that system, watch it respond, learn from that response the kind of behaviors that are encoded in the dynamics of that system. And so this is exactly what both impulses and step functions are representing for us, these actions on our system in which we can learn from the input to the output relationship some kind of dynamics itself. So this is going to be our mathematical way of framing how to do this. Okay, so let's get to this, and let's start considering this system. So we want to start thinking of this object called the delta function. Here it is, delta of n. So this isn't a discrete time system, and you see this comes up in many places in mathematics and engineering. So what it is a function that has the following definition in discrete time, which is it's zero everywhere until the index in here is 0. So when the argument is 0, it takes on a value of 1, and it's 0 everywhere else. So it's a pretty boring function for the most part. There's nothing happen. It's 0, and then at one specific point, it comes on. Okay? So that delta function looks something like this. So here are all your discrete points, and here at 0, it takes on a value of 1, 0 everywhere else. So it's a pretty simple looking type function. It's actually not a function. In fact, when we define this in the continuous setting, this will only make sense in an integral way, which is called distribution theory, which is not something we'll cover here, but we'll be using this, these concepts to start thinking about our systems in general. All right, the unit step function is a little different than the Dirac delta, which is u of n, which is 0 if it's less than n, and 1 otherwise. This is like an on switch. So before n equals 0, there's nothing there, and then soon n is equal to 0, this thing comes on and starts to produce some kind of interesting phenomena. So here, again, it's off, and then it is on. Okay? So that is the unit step. And we've seen the delta function, which is just it comes on and goes back off. These two functions are related to each other. In fact, they're related to each other in some sense through differencing and integration, summation and differencing. In the continuous version, they're related directly through differentiation and integration, which in the discrete case is exactly differencing and summation. Okay, so what is this relationship that we have? So it is related to this idea of integration and differentiation, okay? And let's be more specific about this. So when we think about an interval summation for this delta function, as we move across this interval, so if we sum up to some n, and if we have not hit the delta function yet, then the summation of that integral is 0. Once we move past the delta function, then the sum is 1. So in other words, if I sum over this delta function through this sliding window here, it is in fact becomes exactly this on function. So it's 0 before and then 1 after. So That is the relationship between there. And then the relationship from these step functions, these unit step functions, to the delta function is the following. U of n minus U of n minus 1. Remember that U of n is 0 before n equals 0. So this would be 0. And then, of course, this here is actually turns on at n equal 1. So before n equals 0, this is 0, this is 0. So you add them up, they're 0. At n equals 0, excuse me, here we go. At n equals 0, right here, what we have is this becomes 1, and then this here is still 0, and then at n equals 1 and beyond, this is 1 minus 1. So these cancel out. So this gives you this delta function, which is a spike at n equals 0. So this is like a difference formula. You can think about that as a sort of a differentiation in some sense of that signal. And we'll show this in the continuous case. That's exactly how it's defined as a differentiation. So U of n itself, by the way, then, I already showed you this. It's just the summation over the delta function at some m. So as I integrate over this, this thing here basically takes the sum. If I go back to this picture here, there it is. It's 0, and then once I hit this thing, the area under the curve is 1. So that's exactly what this thing gives you here, is this step function relation, which is this is like an integral, and this is like a derivative. Okay, so that's the relationship between this Dirac delta function and this step function. There are alternatives to do this, right? So right now what we have here in the argument is n. We can always change this over to this notation instead, which is the sum starting from 0. Before I would start from negative infinity to infinity, but I can start from 0 and add this up to n minus k. So this thing will be 0 until k is equal to n, at which point then this thing becomes 1. So the summation hits that 1, and then that's a way of defining that step function. So there's some ways to define these just by shifting around essentially our arguments inside of this variable here. So this is now the representation of this. So if you think about this here, as I'm sliding this in, if n is here, this is less than 0, then when I look at this interval of summation, which is starts at 0, if this thing's less than 0, then it's over here. It doesn't contribute to the summation. But once this thing moves into this region and you're here, the sum is 1. So this is just an alternative picture, basically a change of variable, if you will, from the former way of describing this function. Here is one of the most important properties of the delta function. And in fact, one of the reasons we very much like this delta function, it's the sifting property. And what is it? This delta function is 0 everywhere, except at one point. So think about it this way. Here's my function I'm interested in, x of n. This is my signal in discrete time. And I'm going to multiply it by this function here, which is 0 everywhere, except at one point, n equals 0. So if I multiply any value here by this by 0, it's of course 0. So the only point that contributes to something that is not 0 is when n is equal to 0. And so you can actually think about this as just, it only sifts out the value at x at 0 itself. Okay? Or alternatively, if you want to shift this around here, so you can say, I can sift any value by n minus n naught. So in other words, when n is equal to n naught, this is when this is going to make a contribution to this function here. Otherwise, it's always a multiplication by 0. So that's going to give you here x of n naught. So what the delta function allows you to do is, if you prescribe where you want the value of the function sifted, which you can do right through this argument, it will simply pull that out for you, and that's what you can actually access. So in fact, you can actually write any function as a sum of a bunch of delta functions in this discrete time by sifting their value at every single point. Okay, this is going to be a critical property, as we'll see, both in the continuous and discrete formulations for kicking the system and sifting out values. As I said, this typically makes sense in the continuous case as an integral formulation. And so that's what we're going to move to next, is start thinking about this delta function in a continuous formulation. So here is the definition of it. So it's delta t, and it's 0 everywhere except for at one point t equals 0. That's the argument here. And at that point it's infinity. But not just any infinity. It's going to be infinity in such a way that when I integrate this, the area under the curve is 1. And I'm going to show you how to do this, but basically this function is has this interesting property. It's not even a function. That's why I mean that we have this alternative way to thinking about it, which is called distribution theory, which makes sense of this as a function only provided it's inside of an integral. Okay? But we integrate it to unity. So one way of expressing this is we can draw this function something like this. At x equals 0, or at t equals 0, we say that this thing has a spike going to infinity, which is this thing here. We draw it with an arrow. It's 0 everywhere else. So if I multiply this delta function by any function, it's going to be 0 everywhere, except now right here at t equals 0, I'm going to multiply by some kind of infinity. And the question is, what are the properties of that? And I'm going to define this in a very special way so it sifts out just the value of the function at that location. That's what's special about this. There's also the unit step in continuous time, which is given by here. So it's 0 for t less than 0. It's 1 for t greater than 0. And so there's this discontinuity at t equals 0, right? The function jumps by 1 unit in this variable set. So here's what it looks like. There's the unit step function, right? Takes a little jump there. All right, and it's sort of like an on switch. So when you think about all the systems, we want to think about signal processing. We want to understand what happens if I kick that system or I turn something on. What is the response of the system to a function like this? And if I can understand that, it's going to tell me quite a bit about my system generically, how it behaves over time. Okay, what is the relationship between the delta function and the step itself? And in fact, here, this is even easier to understand, really. It is the integral and the derivative. So think about this here. U of t is just you integrate over this delta function, and this thing is 0 until tau is hit 0. At that point, this integrates to a value of 1, and that's exactly what this thing gives you. You don't get any more contribution once you've gone past tau equals 0. It's because it's just a spike at tau equals 0, but a special spike that has area 1 under the curve. That's the impulse of this, a unit impulse. The delta function itself is the derivative of this function. So in other words, if I go back to looking at this thing, the derivative here is 0. The derivative here is 0. And of course here the derivative is basically, it's a discontinuity. It's like infinity, but it's a very special type of infinity. So you take that function, you differentiate it, you get the derivative is 0 on either side, and it's infinity right in the middle. But it's a very special infinity. In other words, it's an infinity that the area under the curve is 1. Okay, so that's the relationship. And again, this all makes formal sense when you start to consider this under the context of what's called distribution theory, which is a generalization of functions defined in integral representations. All right, so let's consider the kind of functions that we want to make delta functions out of. And let's consider, for instance, a function, f of x, here, for instance, which is equal to 0 everywhere outside of this interval, which is around x naught minus xc and x naught plus xc. So, and in there, the function is defined by f naught x. Okay, so there's a small interval where this function actually means something, and everywhere else it's 0, so that's kind of the function we're defining here. And so notice the following. If I want to define what's called an impulse, the impulse is I integrate over some domain, f of x dx, but remember my f of x is this f naught x, and now it's non-zero just between x naught minus xc and x naught plus xc. Now you already know what I'm going to probably do here. I'm going to start using this idea of calculus to take the limit as xc goes to 0. In other words, if I squeeze this here around x naught, one asks the question, what is the area under the curve here, and what kind of functions do I get out, and how does this impulse integral work? So let's talk about some functions we can consider here. And I'm going to consider a very specific function and a very specific way for this thing to be squeezed. So here's the function I'm going to consider. F of x is equal to 1 over 2xc, and the intervals from x naught minus xc to x naught plus xc. So essentially, this is just a constant function of height 1 over 2xc with width 2xc. So already you know what the area under the curve is, right? It's height times width. The height of this is 2xc, 1 over 2xc. The width is 2 of xc. So those multiply together to give you 1. So this is the special type of infinity, because what I'm going to do now is take the c and take it to 0. So as I take this to 0, this goes to amplitude infinity with width 0. And in this case is a very special case. When you multiply 0 times infinity, you get 1. Okay, so that is the impulse response that we are looking for. So here it is in practice. The impulse, I integrate from x naught minus xc to x naught plus xc. The height of this is 1 over 2xc. So I can pull this out because it's constant, and then I just integrate this. The box size here is width 2 of xc, divide by 2 of xc, and it's 1. So this is what I mean by the special type of infinity. I squeeze this thing down, it goes to infinite height, but the width and the height, when I multiply them together, they are always 1. And it's this unit response that we're going to use to form the impulse that we want for this. And in fact, this is just one possible definition of the delta function. So the delta function that acts around x equals x naught, in other words, this thing is 0 everywhere except for when x is equal to x naught, is defined by the limit as c goes to 0, 1 over 2c over this interval here. Okay, this is just one possible definition. But this definition is very nice. It's very simple. It gives me a rectangle whose height and width and area under that is always 1. And so we can always make use of this. And of course, it only makes sense in this limiting process in the context of integration. Okay, there are other definitions, and here are some that we could use. These are all basically something like this rectangle that as you squeeze it, the width gets smaller, the height gets bigger, but in such a way that the area under the curve is 1. So we have a Gaussian, we have a 1 over 1 plus x squared that we're squeezing down, and then you have something like sine squared x over x squared. And what these look like are just here given in the following boxes. So here's the delta function sequence that we looked at, and it's a sequence in the sense that what you're looking at here is as I take c to be smaller and smaller and smaller, you can see from what we did here, here's the original box, it gets tighter and then tighter. So this amplitude goes to infinity, but its width times height is 1. Same thing here with this 1 over 1 plus x squared type function. I can squeeze it so that the area remains 1 on the curve. Here's the Gaussian. Here is the sine over x squared that we had before. So these are just pictures. They all are equivalent ways to think about that delta function. And so it's not that there's one unique delta function. People study this quite a bit and come up with quite a few different delta function sequences. So you can use ones that are, advantageous for different applications. But for us, we just want to use the simplest version possible, which is this one right here. So let's talk about how the sifting property works now that we have this function defined. And here's how the sifting property works. I'm going to take a function I'm going to integrate over some domain 0 to L, f of x, delta x minus x naught dx. Okay, so I'm going to hit this thing with the delta function. And I'm going to go ahead and take the definition of that delta function. The definition of that delta function is the limit c goes to 0 of 1 over 2 of c. And remember, this is 0 everywhere except for this small interval from x naught minus xc to x naught plus xc. So this should be a minus sign here. Same thing here. So now we can take out this 1 over 2xc, pull it out here. This goes from x naught minus xc to x naught plus xc, f of x dx. And then from here to here, this now, we're going to use the mean value theorem for these integrals to say this takes on a value of the average f of x bar times 2 of xc. So I'm missing a 2xc. The 2xc's cancel and I just get f of x bar. But when I've squeezed it in the limit as x goes to 0, it takes on the value of x naught, right? So that's when you squeeze c going to 0, this becomes f of x naught. So this is the sifting property. So I basically take this delta function, and when I integrate against any f of x, I get back the value of that function at exactly where the delta function, this infinity, is kicking the system. So that's an important property. We're going to use it all the time in what follows, and trying to understand systems when we kick them and perturb them. Watch the reaction to that system so that we can learn something about the dynamics of that system. And the sifting property, this is a pictorial of it. You essentially have some function, and essentially when you kick it, you're extracting the value of that function just where you kicked it. Okay? So, two functions commonly used, will be used by us in quite a bit in what follows: the step function and the Dirac delta function. Both are sort of these important signals that we want to consider in systems so that we can actually learn something about the underlying system we're trying to study by watching these kicks happen and watching the dynamics that occurs after these kicks. And this is how you actually learn a great deal on a system level about whatever engineering design you've put together and how it behaves under these different conditions. Okay, that's it for this lecture. Next, we're going to talk actually more broadly about signals and systems as we go forward in this class.